So welcome boys. In the last session, I think we had this about the polysilenes, a very important structure and a derivative from the silicates. So here is the next point in your syllabus, that is called as the polyphosphazines. They include a wide range of hybrid inorganic-organic polymers. So this inorganic as well as organic is what making it a hybrid one, with a number of different skeletal architectures. That the backbone, that is, we have seen that this has PN, PN, PN going like this. So you'll see the structure there: phosphorus, nitrogen. In nearly all of these materials, two organic side groups are attached to each phosphorus center. So this is very important there. And the linear polymers have the formula of N PR1 R2. Like R1 is any other alkyl group that you are going to attach, where R1 R2 any. I'm going to show you this graphic here, the next slide. So other architectures are cyclolinear and cyclomatrix polymers, in which small phosphazene rings are connected together by organic chain units, and they are available such as black copolymer, star, dendrite, or comb structure. So we are not going to the details, but let's look into the what this basic structure has to do. This is the structure there. Largest class of organic polymers because of each side of group modification. That is, here this is one organic group and this another organic group. And here is the backbone of all the components there. So often this structure is asked. Side groups can be organic and inorganic, or even sometimes it is organometallic, like for example cyanide or carbon monoxide. Method of synthesis I am just going to tell you in the end, but let's look into the uses include why they are very important there. They are included in electrolytes, elastomers, elastic at low temperature, and we have several glues there that become that are there in the form of a paste. When you apply them, they harden. That class of compound is the polyphosphazene. Aerospace and auto application because of resistance to hydrocarbon oils and flame resistance, and even in textiles they are being used. So let us have a look into what actually this preparation is started. Here you have phosphorus pentachloride. I think you know about, you studied in your second BSc about the phosphorus pentachloride, phosphorus trichloride. Phosphorus is a hypervalent compound, that is, it is capable of taking up so many bondings, including 3, 4, 5, 6, 3, 5, 6, and even 7. And if you have a sufficient quantity of ammonium chloride or ammonia, usually you can take the liquor ammonia there. It's very strong, that directly comes with the toluene. So if you put it in both of them, there is a decomposition, and that is a condensation, and that HCl is removed, and you're getting this 3 one PN here, another PN here, and another PN here, third PN here. So all of them are attached to 2 chlorine atoms. And then if you just heat them at 210 to 250 degrees centigrade, you're getting this polymer. So this polymer is called as the polyphosphazene. And you can see that if you take this, okay, here, the center of this particular thing, right? If you take this and place it with a compound like, for example, NaOCH3, you are getting a compound like OCH3 and OCH3 here. This is a kind of a derived polymer, derived phosphazene. Okay, so here it is NaOR, and here you can see amino group RNS2, and then there is a direct substitution of this Cl is replaced by the NHR there. So Cl minus Cl plus NHR here, and here minus Cl plus OR. So these two things you are going to remember. It's very important there. These two things are very important there. Okay, and then you can use any metallic, organometallic here. So you get a PN as it is, then you retain the Cl, and you have some alkyl groups there. So this particular thing, preparation is very essential. So I'll give these notes in the description section. So this is very essential there. And you can see that it can be made to react with uh, aromatic compound like this one here, PHLI. Okay, so here this chlorine is substituted by fluorine atom there, and sometimes this is called as the inorganic benzene. Inorganic benzene, because you got a aromatic system there. Here you have this 2, 3, and this keep on moving like this. Okay, and that is how its reactivity is there. So this is a hypervalent compound here, phosphorus, phosphorus, phosphorus. Nitrogen may not be very reactive, but because of its lone pair, it may involve in some substitution. But usually what happens is this particular part is reactive because of the hypervalency of the phosphorus. The fluorine atom is substituted to give a phenyl derivative. This, when you heat, they again give you PN type structure. Actual, you can see here this is not linear. That is the most important structural parameter about this non-linearity of this compound. So usually when you write, you can just write it as a P double bond N, P double bond N like this, but it doesn't go like this. So it is a kind of bent structure with a pentagonal type. If there is interaction between these two, and that will give you cyclopentane type of structure there. So here below that is given this mechanism. Here it is, that mechanism of ring opening polymerization is there. So as you can see that you are using this inorganic benzene, and you are heating here. When you heat here, this particular one, any particular phosphorus is, because you can see 1, 2, 3, 4, 5 years is phosphorus is pentavalent here, but it becomes a tetravalent there with the formation of a cation here. Okay, this cation is facilitated by another attack from the particular bond there. Because it is a cation here, you can have a migration of this bond because of its instability. If one is becoming charged here, opposite maybe opposite of these particular bonds are vulnerable to become the opposite charge thing like delta minus. So if it becomes delta plus, this becomes delta minus, or there is a nucleophilic attack from here, either from the nitrogen or from this particular bond itself. But you can see this here, this nitrogen nucleophilic attack is being made into this phosphorus atom, and you are getting a bond like this. So this is the newly formed bond there. So when this forms, there is a opening of the ring opening here. So this flips. So the flipping is causing a type of a structure like this. Again, you have got a P plus there. So what can happen is, you can have another nitrogen based nitrogen which is in the ring, and which is like this. Okay, P N like this. So again this may attack here, and this may again attack here. So you can get again a next PN bond there. The dimer is get, and then this is a process of propagation. Chain propagation. The bonding in chain can be explained by the cis and trans conformers. There exists a barrier to rotation. Barrier rotation means it is stopping the formation of the conversion of cis to trans and trans to cis. Cis and trans conformers, the PN bond is very small. However, the bonding in phosphine is still not well understood, though there have been described in the 1960s. But the empirical observation is phosphazenes do not exhibit alternating bond lengths, but bond length is much less than a single pi bond. So it's an important aspect. So what it says is, there was this concept earlier that you have a double bonded system like this, and this bond keeps on moving like this and like this and like this, but this actually doesn't happen. This doesn't happen. So it is somewhere between a single bond as well as the much less than a single bond and something which is much less than missing a double bonded character is also there. So it is supposed to be having a multiple bond character. That means you can have P double bond N and even P triple bond N. So it may exist in between these two or P single bond. So it's a hybrid of these two, and it depends on the type of substituents you're making. That means the hypervalent phosphorus atom is capable of them. Polyphosphines are not colored and do not conduct electricity. That is the characteristic of extensive conjugation. So this is a very important point there. They are not colored and do not conduct electricity. And a very again a very essential point there. You can see that there is a sigma framework there. This you have to write in the examination, and here it is given as the sigma framework with phosphorus having tetravalent and nitrogen divalent. What happens is, this bond will go here and this bond will go here. You will get a double bonded thing, and nitrogen's 3 valency will be satisfied, phosphorus 5 valency is satisfied. These two are stable compounds, but here it is a sigma framework only, and when these electrons are involved it will be a pi bonding system, but still you can have the valency satisfaction there. So the problem of distribution of the remaining valence electrons is becoming very essential, and Dewar proposed the phosphorus 3d orbitals are involved in the bonding. So again, I've been telling you that the phosphorus is not having any 3d orbitals. It doesn't have any 3d orbitals. But as you write, the p orbitals are filled. When p orbitals are filled, the next d orbitals are next. D orbitals are next to these p orbitals, and there is a foray. Foray means these orbitals can move into this d orbitals there. P, this is p and this is d orbital. So electrons can simply, because of the same symmetry here, here and here, some electrons can move into this, and the electrons delocalization can take place, and they are involved in bonding to give PNP island. So they call it as an island. So this is an island there. So this is the island. Okay, so this is the island they are talking about, and this is very essential when you write the examination. And PZ, this is the PZ. PZ overlaps with 3d orbitals. Okay, so this is the PZ orbital. PZ orbital here, this one. This one is PZ orbital, and you can see that this is on d orbital and this is another d orbital. There is a overlapping of this PZ on this side and this side. Actually, if you sit down to look into the p or d orbitals, there is no d orbital for phosphorus, but you can see it has to move into some other next orbitals for making it reactive and bringing all other properties that is due to this p-n bond. So rotation about p-n bond is low energy because the npz can retain overlap with 3 orbitals on rotation. That is, we have seen that this pz is there, okay, and then you have got d orbital here on this side. The d orbitals are there. So sorry, I'll just write it the d orbital there. So there is this overlapping of this p and d orbitals of nitrogen. This is the pz of nitrogen, and this is the empty d orbitals of the phosphorus. This is pz of nitrogen, and this one is that of the phosphorus. So when you have this, there is a rotation around this bond, rotation around this, and it is telling that it is low energy. That means you can rotate them. That is, they can retain overlap with 3 orbitals on rotation. So if this rotation is very having very high energy, then you cannot rotate because you will require a lot of energy and it may break. So that is how this the energy, and particularly because you are PG boys, you have to talk about the symmetry of these atoms, symmetry of these orbitals. You can write that symmetry of these orbitals, they are matching. when there is a matching of these orbitals, they can just flip-flop and then they can rotate really, and they will have low energy barrier. So more recent calculations suggest that ionic bonding appears to be the dominant. So that is, there is always, of course, there are several type of charges to prove charges and atoms. Okay, charges and atoms to prove this, but it is said that there are two types of charges. One is called as the Hirschfeld charges, and the other one is the natural bond orbital charges. So they have calculated this and proved that this is existing in the ionic character, nature, ionic nature. But there is a contribution. But there is contribution from the d symmetry orbitals. I'm not telling the d orbitals, the symmetry, d type symmetry orbitals. There is contribution to this one. So let us have a look into the mechanism that I'm just going to import one picture and tell you what exactly is about this polyphosphazene. Here is the synthesis again. Okay, so this synthesis is what you have to write. You have just seen it. So you take up this hexachlorocyclotriphosphazene. So I just telling you, we have seen borazine also, that this borazine is in inorganic benzene. This is not inorganic benzene, but some people call it as the inorganic benzene. Why you do not call inorganic benzene is the rotation of these bonds are not there. There is no such movement of these bonds there, but when you heat, you get NPCl. This is an important point for you to remember. And then there you get polydichlorophosphazene, which is a reactive polymer intermediate. Then in the step 2, these two things are there. You can use RONA, RNS2 or R2NH, or even condensation takes place and you get OR1, important one, NHR2, important one, OR1 and NS2. So these three are very, very essential for you to remember right in the examination. Okay, and the last part of this is just have a look into the application that is being modernized nowadays. Now the various examples are there, and some of them are industrial secrets also, but it is very easily you can see that how this is taking up the scene there. So you can see there's you started from NPCl. From this they have just added this OR, and this OR is equal to OCH2 CF3. So you can just go on substituting like OCH2 CF2 Cl. Keep on substituting and see that this one is taking hydrophobic film and is used for the fiber forming membrane materials. And then you have the same thing here, this one, but the lower part is you have just substituted with CF2 and CF2H. So there is another substitution there. So this is becoming a hydrophobic elastomer. Remember, this is a becomes a paste at a higher temperature. This elastomer. So it exhibits the property of the elasticity and it changes its temperature. And then you have this aromatic ring there. This is a pH ring there. Both OR is equal to O5. This becomes a hydrophobic film and fiber forming material. So then you have a linear chain there. OCS2, OCS2, OCS3 is there. Then R is equal to OCS2, CS2, OCS2, CS2, OCS3 is there. So slightly organic, I mean the oxygen link is there, ether type link is there, but it is showing a very good property of water soluble property, and it's used as a solid form electrolytes in most of the batteries that come in the mobile phones and other things. So there is only the discussion, I mean the research is taking place in the substitution. You just change our property changes. Okay, property may include the electron retaining property and durability and thermal stability, all those things, and just you can be increased. So here R is equal to OC6H5 COO Na plus is there. So it's a very good water soluble polymer. You want to deliver something with solubility in water, and then it can be deposited in pipes so that at a particular temperature it can exhibit elastomericity, and then it can close holes and you can use. Then You got NH2 we used in the first slide here. NH2 we used. So in the place of NH2, you're just putting CS2COOH, CS2CS3 there. So that is called as the bioerodible polymer. So it can just deposit and disappear. You know what this disappears is being that surgical sutures. Nowadays, after surgery, they just stitch it with this bioerodible polymer, and over a period of time it is getting eroded now removed. It gets eroded as the healing between two skin things are taking place. The the uh, the erodibility, the life of both of these, that is the healing power as well as the eroding power of this polymer becomes. So there is a surgical sutures and after stitching, when these two join, these polymer can simply disappear. So it's a kind of a very essential and very useful. I think you can make a very good research into this in the future and have substituents, and these are all becoming industrial secrets. You are now getting many water sealing paste and water sealing tapes, Teflon tapes, all those things you are calling, and these are the result of a consistent research in the type of the polyphosphazines. Okay, okay. So thank you for joining me. We'll have some other topic discussion next time. See you soon.